In this video, we will find the tangent plane to a parametric surface. So we have the equation for a cone given parametrically in the variables r and theta, so essentially in polar coordinates as given here. And we're asked to find the tangent plane at the point where r is 2 and theta is pi over 4. So first, let's just write what this point is in terms of x, y, and z. So if we plug in 2 and pi over 4 for r and theta above, this will be 2 times cosine of pi over 4 is 1 over the square root of 2. So 2 over the square root of 2 is just the square root of 2. And same thing in the y slot, since sine of pi over 4 is also 1 over the square root of 2. And r is 2. So, the key thing here is that the normal vector to the tangent plane is this vector, the cross product of RR and R theta. So this is the same cross product that we compute when we do the integral for surface area. Turns out that this cross product has a geometric meaning. It's a normal vector to the parametric surface. So once we have it, we'll just write the equation for the plane using that normal vector. So let's compute that. So first, r theta is minus r sine theta, r cosine theta, 0. And the partial derivatives with respect to r are cosine theta, sine theta, 1. And the cross product, which I'm doing in the other order, but it doesn't matter. If you have a normal vector, then any scalar multiple of it is also a normal vector, so the direction doesn't really matter. So let's see. The x component is r cosine theta times 1 minus 0 times sine theta. So r cosine theta. The y component is going to be 0 times cosine theta minus negative r sine theta times 1. So the minuses cancel. This is just r sine theta. And the z component, we get minus r sine squared theta minus r cosine squared theta. So we factor out the minus r, and sine squared plus cosine squared is 1. And here, if we like, we can factor the r out of everything. Okay, so this is going to be the normal vector to our tangent plane. So let's plug in the point. So when r and theta are 2 and pi over 4, this is, so r is 2, theta is pi over 4, then cosine and sine of pi over 4, as we said above, are both 1 over the square root of 2. Which, if you like, we can multiply the 2 in. So this is square root of 2, square root of 2, minus 2. So now we just need to recall the equation for a plane. So we have the normal vector to the plane right here, and a point on the plane above. So the equation for the plane is going to be, so first, the x component of the normal vector times x minus the x component of the position vector, plus square root of 2 from here, times y minus square root of 2 from up here, plus finally negative 2 from here, so minus 2, times z minus and the 2 from the position vector. And all of that equals 0. And so technically we're done here. This is a perfectly good equation for the plane, but it turns out it looks a lot simpler if we multiply things through. So we get square root of 2x plus square root of 2y minus 2z. And if you look at what happens with the constants, here we get minus 2, here we get minus 2, so altogether that's minus 4 so far, and here we get minus 2 times minus 2, which is plus 4, which cancels. So all the constant terms actually cancel out to 0 if we multiply this through, so there's no constant term. And it can look a tiny bit prettier if we just divide by square root of 2 everywhere. And finally we get this nice equation for the tangent plane.